Yeah, hopefully that got through to most people by now. Right, we're going to look at what are called vector fields. I'm going to do two. I'm not going to do it with that pen if it runs out. Here we go. I'm going to do vector fields in 2 dimensions first, because they're easy to draw. But we're really going to be dealing a lot of the time with the 3-dimension as well. Right. Vector fields or vector functions are written like this. A normal function, you plug in an x and y coordinate and out pops a scalar, a number like 4 or 42 or 5x plus 3 if it's a formula like that. But in a vector function, we get things that look like this. So for any given point x, y, there is a vector, this 2-dimensional vector associated with it. So can you imagine that at every single point, although I can't do an infinite number of points, at every single one of these points, there is going to be a vector associated. That vector might go this way, that one might go this way, that one might go this way, this one might go this way, this one might go that way, this one might go that way. Who knows what these 2, 3 do, you know? So can you imagine every single point in 2-dimensional space, there is a vector associated with it. We call these vector functions.
Sorry if I missed this.
Yes.
But I vaguely recall on Friday, you saying something to the effect of like, you didn't think that we'd had enough practice with 15.9 to like do the homework. So you made it not due.
And
it wasn't on the quiz. So I thought.
Oh, that could be true. Did I not put 15.9 in? You're right.
Yeah.
No.
Hold that thought.
Like completely gone on WebAssign, like it just vanished.
Right. You are correct. I am wrong. Hold that thought. We're still going to do that today, hopefully, but let's do some more practice on 15.9, just like you said, which means I have to get it now because I took it off and I didn't put it on. And there it is, ready to appear like magic.
I think that's what I was trying to say in the office hour when I came there.
Okay. Well, glad Tessa's awake and I'm not. So here we are, 15.9. Let's finish this guy off. 15.9, change of variable. So see what that one looks like. So what you've got to do in a change of variable basically is that you've got a double integral of some region R of some function f of x, y, and you're going to integrate it with respect to say x, y, but when you use x's and y's, it's either very difficult to describe the region or the integrations you get are really ugly and you can't do it for that reason. So you essentially change the subject, that's change of variable, and you get another integral in terms of some other, I'll call it S. And you do
the change of variables assignment. It's actually the original change of variables, not the one that we were doing examples based off of on Friday.
Was it? It's the one I've got in front of me. I don't know I had 2. Do I have 2?
Here, can I share my screen so I can show you?
Sure. Let's see. Let's get Terence in and see what else I'm getting up to. Right. Give me a second and I'll let you share. Okay. Should be able to share.
It has one of these like graph
Uh-huh.
questions, which we didn't cover.
Right. So that's where we're going to go. Gotcha.
Integrations.
Yeah. Yeah, these are the ones I'm looking at in front of me as well. So we are in the same spot.
Is this one here with the graph?
Right, we got a couple that's questions 1 at the top, right? That has a graph, right?
Correct.
And a couple of transformations, and then we have some guys at the end, which are just the typical this fella here. Okay, yeah, I'm cool. I know what I'm doing.
Okay.
I'm not going to have to take back attention. So, where were we? We were talking about change of variable. So you've got a function in terms of X and Y, that doesn't work for various reasons. So you change it into a function using U and V, and that's a Jacobian. This here is the X gets turned into some in terms of U and V, and so does the Y. So I think I should pick one of these guys just to go through that, and then we'll show you the region ones at the top that we haven't covered. So in this particular one, might as well make it. I hope I haven't done 14. It's a double region, a double integral of a region R. The function is 10x plus 10y dx dy. And it's a parallelogram. That seems familiar, but that might be because so is 13 a parallelogram. Yeah. Well, they all are kind of different. What do I want to do? I don't want to do a parallelogram because we have done those. Okay. Change attack. Question 12 is not a parallelogram. It's still a double root integral, region R. It's 7xy. We're going to do that fella. And we are going to switch it because the region R is described as y equals 1/2 x, y equals 2x, xy equals 1/2, and xy equals 2. And then they describe the transformation as x is u over v and y equals v. I think that's everything. Right. Okay, that's just the basic information. So we are going to have to find the Jacobian. So I'm going to do that first. Do it over here. And it's going to be the derivative with respect to x. Oh dear, I tell you, I am getting too old for this game. Today has been a very hassled day for me, and I am already thinking that I am in trouble with my wife because today is Valentine's Day and I forgot to get her stuff. So I am already thinking, how the heck can I get out of here, grab some stuff and have it in the house before she comes back? And
Uber Eats.
Uber Eats. Oh, you mean deliver food? That's possible. Okay. I was thinking something.
Somebody
There we
should
go.
start a business that just delivers like emergency Valentine's Day and emergency birthday presents.
Oh God,
Like
tell
a
me about it.
Stock of random stuff.
Okay, now in this story, which I keep bouncing about with 3 versions, we've got our Jacobian set up. I was trying to get the thing the right way around and I didn't. So I'm going to differentiate this guy with respect to u, and that gets me 1 over v. And this guy with respect to v gets me negative u over v squared. This guy with respect to u gets me nothing. And this guy with respect to v gets me 1. And so when we do the old major take away minor, doesn't end up being very simple. Now, in this particular question, we've got these 2 guys going on, right? So we need to figure out how to transfer this information into limits of integration in terms of u and v, right? So first step I would almost always do is get the Jacobian. Second step I would try and do is get the limits of variation, limits of integration. Now, when it was, you know, when it was one of those four-sided shapes, didn't we just find the equation of all the lines, and that became, u became 0 to 2 and v became 0 to v minus 1, whatever it was. I don't have that information, but I do have x is equal to u over v, and I do have y equals v. So if I take each one of these equations and replace the x's with this fella and the y's with that fella, I should be able to get the limits of integration out of that. So if you start with y equals 1/2 x, and y is v, and it's 1/2 u over v. So far, so good. I'm going to rearrange this, and it becomes 2v squared equals u. And that becomes v equals u over, or v squared equals u over 2, and that becomes v is the square root of u over 2. Now I'm taking the other one, which is y equals 2x, and that's going to give me v equals 2u over v, which is going to give me v squared is 2u, and that's going to give me v is the square root of 2u. So I now have the limits of integration of v, and they're in terms of u. What we're going to get here, the big one is probably this guy, yeah, and the little one is this guy. Now, if you take the other one, which is xy is 1/2, and you put in x, which is u over v, and y, which is v, you get u equals 1/2. And then if you do xy equals 2, you get u over v times v equals 2, and that gets you v, sorry, that gets you u equals 2. And now I have those guys. So I now have the limits of integration, not in terms of the original, you know, x's and y's like these guys, but in terms of u's and v's. So I should be able to put that package together now and come up with what the integral looks like. Originally, it was a double integral of 7xy dx dy. It's now going to be a double integral v from the square root of u over 2 to v equals the square root of 2u, and u is going to be from 1/2 to 2. 7xy is going to become 7, x is u over v, and y is v, times the Jacobian, and the Jacobian we found was 1 over v. And then we can do a dv du. So let's see what we've got. That's 7xy. That's the Jacobian. That's the new variables. And these are our limits of integration. So if I tidy it up just a little bit, it's going to be the integral from u equals 1/2 to u equals 2, and then from v equals this square root to v equals that one. Cancel, what have we got? 7u over v dv du. Are we good with that? Any questions so far?
With that, the only sad thing is that we'll have an integral with a natural log.
Yeah, you're going to have some natural logs and stuff, but it is doable, right? You could do it. So that was the end of that one. I think I'll do another one.
They probably need to use
Like
the table
this.
of integration.
I'm looking at the answer. No, it just ends up being ugly logs. So you only need to do logs, and then it comes out reasonably nice. So this one, again, I'll set it up as a version.
Screen.
Oh, Was I showing the screen for any of that time? Was I just talking to myself?
We saw
Okay.
the map, but then he stopped hearing with the after you finished that problem.
Ah, okay, so I didn't waste it. So the next one is a version of 13. It's going to be 7x add y e to the power of x squared plus y squared. And we have got a rectangle described by x minus y equals 0, x minus y equals 4, x plus y equals 0, and x plus y equals 3. And we are going to do a change of variable. This one is harder because no one has told us who the guy u and v are going to be. Right, in the previous question, they told us, you know, y was v and so on and so forth. Right, I got this guy. There is a very big clue here. If you've done enough of them, you'll start seeing it. Do you notice that these two ones have x minus y in them, and these two ones have x plus y in them? Do you see that? Then to me, a natural choice would be that. Great. Make u x minus y, make v x plus y. Because, well, for one reason, does it not make the limits of integration very easy? And the Jacobian, not that bad. I always get that damn thing the wrong way around, don't I? But this time I did it the right way around. Now, do you see in this question, the information is not x equals some function of u and v and y equals some function of u and v. It's this way around. You see that? Now, there are two ways to approach this. The long way to do it is to take these two equations and solve for x and y. Well, I'll show you how that works. If you add these two equations together, u plus v ends up being 2x. So 1/2 of u plus v ends up being x. And once you know what x is, you can place it into here. And so u equals x take away y, u equals this fella take away y equals this fella take away u, and y equals 1/2 v take away u. So I know what u and v are in terms of x and y, but for the Jacobian, I would need to know x in terms of u and y, and those guys. So I could differentiate this with respect to x and y, differentiate this with respect to, I'm saying differentiate this with respect to u and v, differentiate this with respect to u and v as well, plug it in here and get the Jacobian, right? And that would work. But I want to show you a shortcut. Instead of getting that Jacobian that way, when the terms are linear, you can actually find this Jacobian, right? Sorry, this Jacobian. I am not good at multitasking. Right, you got this fella. So all I need to do is do this fella with respect to x's and y's and then turn it upside down. So let's see what that would look like. Do this with respect to x and y, and do this with respect to x and y. With respect to x, this guy is 1. With respect to y is -1. With respect to x, this is 1. With respect to y, this is 1. You get 1, take away -1 is 2. You get the answer is a half. So the Jacobian is a half. Can you trust me that if you did it this way, you also get a half? And just a quick shortcut. That if you want to find a Jacobian, you can find the reciprocal Jacobian and it's the same thing. In other words, switch the x's and y's around, or using these in this case, and do that Jacobian. Well, that means I've got everything I need then. I know the integral for u and v were 0 and 4. And for v, 0 to 3. I know the Jacobian is just a half. And then 7x add y. Well, 7x add y becomes 7v. And e to the x squared plus y squared. This guy here needs to be turned into u's and v's. How would I turn x squared plus y squared into u's and v's?
Would it be u times v?
Oh, I wish that was true. That would be x squared minus y squared.
Oh,
And
oh,
oh, by the way, the good news is it is x squared minus y squared. If it had been x squared plus y squared, I would have taken this ugly guy squared, plus this ugly guy squared, and combined them. And I think you end up with u squared plus v squared. So it's almost like, you know, pretty simple. Right, there's your integral. You want to tidy it up a little bit. At least the variables are separable here, aren't they? Are they? Yes, they are. The variables are separable and you should be able to get your answer. Our next fella is question 1. And we'll be given a region S in terms of a variable u and v, such that u takes values from 0 to 4 and v takes values from 0 to 3. And we're given that x is equal to 2u plus 3v and that y is equal to u take away v. And we are going to take this region and find what they call its image. What they're after is, what does it look like in XY space? So I'm going to draw a little picture of what S looks like right now. If I call this the U axis and I call this the V axis, we go from 0 to 4 and we end up with this guy. And that's what the shape looks like in UV space. And we're going to take this shape and we're going to figure out what it looks like in XY space. So what we're going to do is we're going to take all 4 sides. Let's start with that side there and figure out what these things look like when you convert them, all right, into X's and Y's. So this vertical line here to here, okay, isn't that U equals 0 and we only use it for values of V from 0 to 3. Would you agree that that vertical line can be described in this format? Right, U equals 0, vertical line, but only using values from 0 to 3. Now, if you take the x equation, excuse me, and the y equation, and you put those guys together, we can do a transformation. Excuse me. So x is equal to 3v and y is equal to negative v. So I'm replacing the u's here, right, by zeros. So far, so good. Now, what we have to do is take these two equations and combine them in terms of y and x. Right. Okay, so a couple of ways of doing that. Wouldn't the simplest way to just say that x is, whoops, is that, let's try that again. X is 3v and y is negative 3v. So if I take this,
negative 3v.
yeah, I'm taking this guy. And so y is going to equal, what if you combine this information with that information? What is y going to be?
Negative x over 3.
Yeah. So let's see if I can prove that to you. I keep trying to skip the variables around. V is x over 3, and y is the negative of v. It's a negative x over 3. Does that make sense of where that came from? Right, so we know that we're going to be looking at a line y equals negative a third. So basically we're picking a line that's roughly in that direction, agreed? Goes through the origin, slope is negative 1/3. Now, it can't go on forever, doesn't it have to stop somewhere? Right? So how do we know where it stops? Well, if v goes from 0 to 3, what does that mean that y does? Well, doesn't the y go from 0 to negative 3? Oh, so I've actually drawn my line. Well, 0 to 3, y goes from 0 to negative 3. Oh, it's not the y's we're interested in. Although that's true, it does go to negative 3, so I guess I can use that. Can you see it stopping there then? Does that make sense? I better put it the right way around. So what I have got is that that guy is this line. And since this is from 0 to 3 and y is negative v, y goes from negative 3 to 0. Right. Now, you take any one of the lines that are left and you kind of go through that same process. I'm looking for a different color, but I can't seem to find any green. There we go. Let's take this line along the bottom. Now, this line has the property that v equals 0 and that u goes from 0 to 4. Now, if you make v equals 0 and you plug it into the top equation, you get x equals 2u. And you plug it into the bottom one, you get y equals u. And if you put those together, don't you get y equals 1/2 x? Are you happy about that? Or shall I show you the working? When u be a half of x, so y is u becomes y is a half x. So I know that this guy, the green one, is y equals a half x. And what else do I need to know? I need to know where does it start and where does it finish? Well, if you tell me that y equals u, then isn't this going to be y goes from 0 to 4? Do you see we now know to stop at 4? Right. The line y equals a half x. And u from 0 to 4, well, u is the same as the y coordinate. So if u goes from 0 to 4, So does y go from 0 to 4, so we get this guy. I know what the next two are going to do, and it'll take me forever and a day to do it. Can you trust me the other two look like that? So if you took this line, and then lastly that line, you would generate one of these, and the other one would be that. And one of these pictures looks just like that, and I believe it's the second picture. But you can check it out, because it could be the first picture now that I'm looking at it. One says 8.3, one says, okay, what would that be? 4. Okay, it is the second picture. I was right. That's basically it. Well, I could spend another day on these, but unfortunately we don't have the time. Well, let's return back to a totally new topic, our two-dimensional vector functions. So to remind you, any point in 2D space, this vector function gives you a vector. So at every single point, there's a vector pointing in some general direction. And we call these functions vector functions. And this picture, the whole picture, is called a vector field. Now, there's a whole bunch of questions about drawing vector fields. Can you trust me? You don't want to do this by hand. And we have some software that's going to do it for us. So I have got it set up. I just need to find out where the thing is. And we are good. Right. Okay, let's show you where it is. So it's not the picture I'm looking for. Okay, I'll have to go back out and in again. And 264. And check. Okay, are you looking, well, what are you looking at right now? You should be looking at 264, are you?
We're looking at Canvas,
Yes.
Okay. Okay, now I'm clicking on our class, which is 264. Is that the one you can see, or should I be back out and in again? Oh, you could see it. Darn it, I shouldn't have done that then. Right. There's the solutions to the midterm. And here is a vector field in 2D. So let's do that one first and show you the kind of funny way that you do it. The vector field is basically described as the x component and the y component, and these x's and y's are the coordinates of the point. So what you're looking at here is a two-dimensional vector field that has the equation that the x component is x squared take away y squared minus 4, and that the y component is 2xy. Can you see why vector functions and vector fields are very good at representing flows, magnetic flows, electric flows, currents in the river, wind flows, and so on. But this is a 2D one. If you wanted to put in a different equation, for instance, if I wanted to just do x squared plus y, you put that in there. Let's suppose I wanted to call this x minus y. Can you see that this particular vector field has got, that's quite interesting what it's doing. If you look at these two quadrants, aren't the vectors all heading towards the origin in some way? But what's happening on this side is that they're leaving the origin and there's some kind of curve thing going on. So to me, this would be things coming in from the left towards the origin and then exploding outwards to the right. So that's what this is modeling. You can tweak these things because on the length of the line is an indication of how long, how big the vector is. So that could be an indication, for instance, of the strength of the wind. Or a vector field, if you were thinking vector fields. In fact, whenever you stick the word field at the end of something, it's probably going to look like one of these. So if you move this fella around, can you can make differences to how many XY values you do. If you do this one, you can make them bigger or smaller or almost non-existent. So that guy is for two-dimensional vector fields. So if you get a question and they ask you to draw one, you're going to go here. There are going to be 4 pictures. You pick the one that looks like this guy. Now, there should be also an even more complicated version, which are vector fields in 3D. So I want you to imagine that every single point in X, Y, Z, right, in 3-dimensional space, there's a unique vector pointing in that point, and it's given by an equation that looks like this. I, J, K. I is the X direction of that vector, J is the Y direction, and K is that one. So if, for instance, if I make this X, if I make this, say, X plus Y, and then I make this X plus Y plus Z, you are now looking at a 3-dimensional vector field. Now, if you find that the lines are just too long, you can shrink them back a little bit. There, and a little there. Maybe a little bit too much there. Now, you can also rotate this. For instance, if you look at it straight above, don't you get a better impression of what the heck is happening here? Isn't there a kind of, I don't know, turning motion going on? Can you see the vectors keep going in a kind of anti-clockwise direction? That's kind of interesting. If you look at it face on, and you see there's a kind of going from left to right, branching away from you. So this here is modeling quite a complicated situation. It looks to me like a kind of spiral. Can you imagine water going down a plug hole? It's kind of like that. That's what I'm saying when I say that.
There's
So,
symmetry in it too.
There is a lot of symmetry. Agreed. Now, if you take one of the simplest ones, which is x squared, right? So the vector is made up of the x component of vector is the value of x squared. The y component is y squared, and the z component is, say, z squared. This is quite an interesting fella. Oh, now I think I need to shrink these a little bit, or make them bigger. Shrink. There. That's a very interesting vector field. It's not chaotic. If you really focus on one direction at a time, there is an awful lot of symmetry in that shape, isn't there? This one can be quite interesting. I don't know if this will take a sign. I hope it does. Please take a sign. There's the sine of x. The cosine of x. And the sine of x plus the cosine of x. Or cosine of y, I should say. Maybe make the thing a little bit bigger. That is fascinating. That is not random. It might look like it's higgledy-piggledy, but it's really sinusoidal. If you did a lot more points, you would see like waves of sines and cosines interacting with each other. It's a bit like two waves clash together and then they kind of do some real mess at the, at the point of contact. Really fascinating things. I could spend days looking at these things, but we don't have days, unfortunately. So let's return back to the nitty-gritty of vector fields and what you can and can't do with them. Right, well, we've shown you a 2-dimensional one, a 3-dimensional one, would just look like this guy. There's an example of one. It's got 3 vectors. And we have 2 sets of software. So when you get questions like, here is a vector field, here is a vector function, which one of the 4 pictures is it? Well, you go to one of those 2 guys we talked about and plug it in and maybe adjust it a little bit, and you should get, where is everybody gone? I've lost you all. Oh, you're still here. For one moment, you all disappeared on me.
You were flawless the whole time.
I was here. Okay, good. Let's move this thing out the road. So computation, nice easy question. This is a version of question 1 and 2. I'll make up my own vector function. Let's suppose our vector function that says at the point x, y, z, the vector that you get at that point is given as x, y, and 2z. If you're asked to find the value of the vector at a given point, let's suppose at 1, 2, -1, it's as simple as x is 1, y is 2, and there's your third guy. Would you all say that I would have done that anyway? That's pretty, intuitive. That's how you find a one specific value of a vector function. Now they could give you the vector function like this. Okay, remember the I, j, k's? I is 1 in the x direction, j is 1 in the y, and k is in the z. I don't like that notation. You know how easy it is for me to get confused. I much prefer it that way, which is exactly the same information, right? It's just easier in my brain when I write it that way. So I almost always turn questions into that. If you were given this fella and you were being asked to find at 1, 0, 3, for example, you would get 1, 0, and 9. So at any given point in 3D space, are you comfortable that you could evaluate the unique vector that you would get? Now, when you're typing in your answers into WebAssign, when you click on the little box, the thing, I think it's called CalcPad, that guy, you have to scroll to the one that says vectors. And in the vectors, you'll get a guy that looks like that, which is the one you press if the answer has to be like this. But you also get boxes called I, j, and k, and you have to type them in. So just pretend that the answer was 3i plus 2j plus 4k, right? Let's suppose that was the answer. You cannot type in 4i on your keyboard. If you do that, it will tell you you're wrong. You have to use these guys. So they are specific buttons in CalcPad, even though that looks exactly the same thing. And when you type it in, all you'll see is that. I think they might make it a little bit bolder, which is what they should have done. Just a little hiccup, because you might be doing the right answer as I, j's, and k's, but it ain't telling you you're right, and you're thinking what's going on. And the same thing's true if the vector function happens to be written, like this. You have to use these guys as well when you write it in that format. If you're being asked to write it in this format, which I find a lot easier on the brain, looks like that. Okay, so what should we have got today? There are 2 pieces of software, one for doing 2-dimensional vector fields, one for doing 3. You just plug them in, you look at the picture, you can tweak it a little bit, and then you pick from 1, 2, or 3, 4 pictures which one it is. And the next thing is, how do you evaluate it? So the questions that involve sketching. There are questions 3. I'm just scrolling through them. 4. 5. Yep, still on sketching. 6. This is going to be very quick homework. By the way, 6 is 3D, not that really much too much. And that's it, right? So those guys. Do you want me to go back to that software and pick one of these to show you how it's done, or do you think you could figure it out yourself? What do you want? Do you want to see one done? One more? Not bothered?
I'm good.
You're good. Okay, we'll move on. Now we're going to look at a guy called the gradient vector. Remember that guy? Remember Lagrange multipliers, Tessa? I know you don't like Lagrange, but you know them, right? You recognize the symbol. Okay, so what you're going to get, and this starts off at question 7, is you're going to get a function, a normal function, not a vector function. In this case, it happens to be that guy, right? And you're going to find the gradient fella. And it's a partial derivative with x and the partial derivative with respect to y. And so the gradient function, right? It's this guy here. It's called the gradient function. Isn't that an example of a vector function? Right? So isn't the gradient function just an example of a vector function? In other words, for any given value of x and y, won't you get a vector associated with it? So let's see what the gradient function on this question is. If you differentiate this guy with respect to x, you're going to have to do a product rule. So it's going to be 1 times e to the 9xy plus x times e to the power of 9xy times the derivative of that, which is 9y. And if I tidy it up, then it's e to the 9xy, oops, comma, there's a comma there, comma, 9xy e to the 9xy. And that is your gradient function. There we go. Let's try a gradient function in 3D. Yeah, this one will do. No, we won't.